right, so we just finished on a piece of pencil and paper, this example about why your cell phone isn't going to kill you. And I'll go ahead and post the full lecture PowerPoint slides. I made them a little wordier than I would otherwise make them, so that if you want to follow along with the video of what we did on pen and paper, that's great. If not, you can also follow along just by looking through the lecture PowerPoints. Might be an easier way to study so that you're sort of way that you're more used to studying. Your book starts off with a discussion of what's called Maxwell's equation, and basically every geeky physics major, this is how I know that I wasn't a geeky physics major, has had a t-shirt that looked like this. Says, and then God said these things, and then there were light. These are Maxwell's equations. These are the equations that describe light in a calculus class. And we've actually covered much of Maxwell's equations while not actually talking about the calculus of them. But the main point here is that this discovery of electromagnetic waves and the full understanding of the way that light propagates is still 100-year-old science, but it's only 100 years old. Maybe it's a little bit older than that. Also 100 plus a few years old. This is a pretty profound discovery to have sort of understood the way that electricity and magnetism are the same way, and actually the way that they propagate is through light. Is a pretty neat discovery. Okay, so just to get some things that are visual that I am not artistic enough to be able to draw on the board. This is a three-dimensional view of what an electromagnetic wave looks like. So we have a wave propagating in that general direction, and we have sinusoidal oscillations of both electric field and magnetic field happening at the same time. So the wavelength of the electric and the magnetic field is identical, right? The place where they are nodes, where they cross zero, happens at the same time. The place and time where they have maximum amplitudes also happens at the same time. So what we actually have here is that sort of electric and magnetic fields are oscillating up and down and up and down and up and down as they propagate down the line of this. This is a transverse wave. It looks just like a transverse wave, right? Transverse waves happen because motion, here we don't have actually motion of matter, but I'll still refer to it as motion, is happening up and down as compared to a longitudinal wave, which would be if the wave was going like that. And everything here is perpendicular to everything else. So electric field, magnetic field, and actually propagation direction are happening in all three directions. So here we have electric field, magnetic field going out of the page, and speed going in another direction. So there is a right-hand rule here for figuring these things out, but we won't use it. And I had a quick video that is maybe a little easier. Where maybe you can see that. Sort of motion is going up and down as the wave propagates in this direction, and electric and magnetic fields are oscillating. I'll show you that one more time. All right, so it wouldn't be complete if we didn't do a couple of quick checks. So here is a fun one for you to summarize some things. So we've spent a lot of time talking about fields as being these sort of mathematical constructs that help us visualize what forces charges would feel if they were placed inside fields. So the question is, are these fields real, or are they just things that physicists made up to help us sort of conceptualize what's going on? So chapter 16, we learned that force is electric field times charge. You need the electric field and a charge to feel a force. Chapter 20, we learned, this is the motional EMF equation, that the magnetic force is a charge times its speed times the strength of the magnetic field. So you need both a magnetic field and a moving charge to feel a magnetic force. So, are these real things? Are these fields real things? Or are they just things that we've made up to help us visualize stuff? So the answer here, which may be surprising, is that these are actually real things. Electromagnetic waves are oscillating electric and magnetic fields. And one way that we can prove that they are real is that they are able to transmit energy, right? The radio waves coming from your radio tower have to be transmitting energy, otherwise how would they make an antenna receive it and play radio waves on your radio? So the fact that these electromagnetic waves are carrying energy is proof that electric and magnetic fields are actually real things. They're not just things that I made up to make your life more difficult. And what do you want to do to double the intensity of an electromagnetic wave? So hopefully you have open either the equation sheets or the notes that you just took from the rest of this online lecture. You can look through this. All right, so somewhere on your equation sheet, you have that the intensity of the wave depends on the square of the electric field. It also depends on the square of the magnetic field. So if we double that, then we'll actually take the square root of that. So here's that, which is that if you have E is proportional, or I is proportional to the electric field squared, then the electric field is proportional to the square root of the intensity. So if you double that number, then you've actually only taken times the square root of 2, which is 1.4. So there's your answer. And that's all I have for this. So we will pick this up in class on Tuesday and go from there, finish off chapter 20.